and a warm welcome to everyone joining this session. I welcome you all on behalf of Sri Rapid Technologies. I am Sonal Khoth, Assistant Marketing Manager at Sri Rapid Technologies, and I will be your moderator for this session on rapid prototype molding with 3D printed molds. The agenda for today's session is introduction to Sri Rapid Technologies, followed by we will have a introduction of the speaker and the webinar, and later on we'll have a short interactive poll where to gather your insights. Basically, at the end we will have the Q&A session, but I request all the attendees to drop your question in the Q&A sessions during the webinar, and we will take it up at the end during the Q&A session. So to begin with the introduction of Sri Rapid Technologies, founded in 2007 by our founders, we have a complete digital manufacturing workflow with an experience of 70 years in additive manufacturing. This is a complete workflow we follow from reverse engineering, designing to post-processing process. Currently, with a footprint of around 17 years of industry experience, we have done around 850 installations pan-India and pan-India presence with a technical and strong technical and application experts and a dedicated team around India. We also have a customer innovation center for metal and plastic. Basically, here we do basically prototyping and also provide customers to come and see the live machines and live processing or the parts, live demos. Additive manufacturing, we have basically a strong full spectrum of AM technologies like SLA, DLP, SLS, MJP, Triple F, and more. We also have a wide presence across multiple industries, and customers across industries can come to us with their with the requirements, and we can provide them the solutions. We have vast experience of around OEM partners, like we have global OEM partners with us to provide the 3D printing technologies from start from reverse engineering to post processing and softwares as well as 3D scanning. So after this short introduction, let me introduce you to our speaker, that is Laz Tal. So Laz is the CEO of 3DP Molds and also co-founder of AddifFab. He is a pioneer for freeform injection molding, enabling one design cycle and complex part. With nearly a decade of experience in 3D printed molds into traditional tooling and injection, a strong advocate for accelerating product development cycles using digital manufacturing. Currently, he is leading 3DP molds to accelerate with the mission to make 3D printed molds mainstream production solution. We are thrilled to have him here and share his expertise with a global perspective on rapid mold production. Without further delays, so let's begin with the session. And now I invite Laz to take us through the session. Laz, the stage is yours.
Thank you, Sonal, and thank you a lot for hosting me today. I have been very much looking forward to being here with you. 3D printed molds, as you can probably imagine, is one of my favorite topics. And in the presentation today, I will be reviewing, of course, the rationale behind 3D printed molds. I will be sharing a lot of application cases with you, but the main objective for me is to actually ensure that you get to answer the questions about this technology that you may have. Because 3D printed molds is a slightly different approach to 3D printing than other topics we have. Now, let's see if I can get this presentation to work. So, as also mentioned by Sonal, I have founded the company AddifFab, and that's where the roots of 3D printed molds for me began. I've built a business and a career on supporting applications of 3D printed molds because I believe it to be a very powerful combination of technologies that are universally adoptable in the industry. My key priorities as a company owner and as your supporter is to help you implement in the format that you need to implement 3D printed molds, because I want to help you reduce the cost of operations. I want to reduce the cost of being wrong, basically, which means we are also reducing the cost and risk of development. And I want to streamline the decision-making process, because when we develop new products, a lot of what we are spending our time and energy on is basically figuring out how to avoid being wrong. So my goal here today is to help you assess whether 3D printed molds might be relevant for you, and to share some experience from other companies working intensively with 3D printed molds. Now, the first question that we need to ask ourselves before starting the dialogue about 3D printed molds is, why do we even want to do it? And for me, the answer has two components. The first component has to do with some known limitations in the world of 3D printing. We cannot always get access to the materials we want to use, and even when we can access the materials in a 3D printable format, they will not perform as injection molded materials. And this means that 3D printing is a very powerful technology for prototyping, where we need to explore part concepts, but it's not easy to move from a prototype to a produced part if you cannot get the materials you want to use or the quality of the parts you need. On the other side, you've got injection molding. You've got a wide range of materials. You've got a universal deployment of powerful machinery, mature industrial supply chains. But the cost of molds and the time it takes to design and manufacture a mold is a prohibitive barrier for prototyping. And this means we face a situation where our prototyping technology cannot really deliver the materials and the quality we want, and the production technology cannot be used for low volume manufacturing or prototyping. But by integrating 3D printing into the injection mold manufacturing workstream, we can actually combine the two best things about the technologies, namely the flexibility of additive with the scalability of injection molding. And this is what I've been spending the last 10 years exploring and proving out in practice. I've done more than 800 projects by now, all projects involving the design of molds for parts that need to be injection molded across a wide range of industries with a wide range of different materials. And I have a very extensive network of manufacturing companies who have already implemented, and some are also ready to start offering services based on 3D printed molds. The workflow of 3D printed molds starts, of course, with the design of the part we want to mold. And once we've designed the part and checked everything we need to do about the part, we can translate it into a mold. It's important to remember that injection molded parts require molds, and that molds may either be simple structures that are closed to form a cavity and opened, or they may be complex structures featuring side action and collapsible cores, because the part we need to produce is complex. This is one of the things we want to address with 3D printed molds. We don't need complex molds in the prototyping stage. Prototypes are focused on parts, not necessarily molds. And for that reason, our objective with the 3D printed molds is also to reduce complexity. We do that by using a combination of soluble and non-soluble mold materials, because by using soluble materials, we can avoid problems with undercuts and through holes and other features in the part that would normally require mold action. So we design the mold as simple as we can. And then, of course, we print, clean, cure the mold elements. We injection mold using conventional injection molding machines, using conventional injection molding materials. And then we need to get the part out of the mold. And that is either by conventional splitting of the mold, where that is possible, or by dissolving those mold elements that are not easy to remove from the part. The innovation of soluble mold elements was one of the key innovations powering Addifab, which was sold to Raise3D, because we had that unique ability to do soluble injection molding tool elements. But it is very attractive for cost management purposes to not have to dissolve the entire mold. And that is one of the reasons why I have developed 3DP molds to also encompass other materials, to encompass easier to design solutions. But this is the basic workflow. When you as an organization want to start exploring 3D printed molds, you basically have to think about 4 things. The first important thing is you need to have a suitable application. If you can already 3D print all your parts and are happy with that, or if you already injection mold all your parts and are happy with that, there is no reason to start exploring 3D printed molds. But most of my customers are in a situation when they need to develop new molds, need to develop new parts. And in order to manage the complexity of the mold and part development process, they use 3D printed molds. But it's important to keep in mind that 3D printed molds is not necessarily a serial manufacturing tool. It's best for prototyping and low volume manufacturing, and it's best where speed and low costs are essential. So I usually see companies implement 3D printed molds for the prototyping of injection molded parts. The next thing you need to be aware of is that you of course need to work with a reasonable quality of printing, because when you are printing molds, they are usually not single item objects. They usually need to be assembled, and this means you need to have a good precision, repeatability, good tolerance control. In order to be able to provide the necessary flexibility, you also need to have open access to materials. Of course, I understand that some of the printer manufacturers have developed business models that are based on total integration of printer and materials, but I like to be able to offer flexibility. And I also like to be able to offer the opportunity to do both 3D printed parts, injection molded parts, and hybrids. And that means that I need open materials systems. And then I need systems that have a well-designed workflow. If I'm leaving everything to an operator, then that operator may or may not recall what is important in a specific job. But if my printer system takes care of the workflow, then I don't have to be worried about forgetting things. On the molding side of things, I like flexibility. I'm operating pretty simple machinery in my own shop. I have manufacturing partners who operate much more complex machinery. But for prototyping, think about getting stuff that is easy to use and has low changeover costs. I sometimes see injection molding companies thinking about adding cooling to 3D printed molds, for instance, and that does not really make sense. So you need to think about the entire chain. Do you really need all the complexity of a fully blown injection mold machine for the prototyping, or can you make do with a little less? That's always an important question. And then of course you need somebody in your team who understands the process, somebody who may be able to design, print himself or herself, or may be skilled at making requirement specifications for outsourcing. But at the end of the day, implementation shouldn't be a complex process. So if we boil down what I've just been telling you, the important thing is to determine, do I need this technology? And if I conclude that, yes, I'm going to be developing injection molded parts, then think about whether you want to own the solution yourself or whether you want somebody else to do the printing and molding. Because both alternatives are out there and I can help you either way. But of course, If you want the fastest, cheapest development of products, in-housing is a good alternative. If you're doing only occasional print jobs, mold jobs, then in-housing may not justify the effort involved. So consider, how do you want to implement, whether to do in-housing or outsourcing. We can help you with both. And if you move through the implementation of 3D printed molds in your product development, what should you then expect to gain? Well, the first thing, of course, is lower costs, because you don't have to start cutting metal. You don't have to start designing complex molds. You don't have to start the outsourcing and capital allocation processes that are normally associated with mold investments. Because you can print molds, you also have a much easier iteration process. You don't have to tie yourself in with a specific design. You can explore multiple different designs at the same cost of a single metal tool. And you don't have to spend so much time persuading management that a given mold investment makes sense, because the mold investments are lowered significantly. You should also expect much faster times to market. Again, designing a mold is one thing. And if the mold is used for a complex part, you have a lot of things to take into account. You also don't have to spend time on investment decision making. You don't have to spend time waiting for the mold to be manufactured. And this means that your entire time to first part is compressed. I've participated in a study where we had to injection mold 4 parts, and we had Deloitte, the accounting agency, do the mathematics for us. By using 3D printed molds to get the first prototypes out, we were saving more than 80% on the costs and more than 80% on the time. We were also greener by a factor of 4, because we did not have to start cutting metal, and that means we don't pollute as much. Finally, by using 3D printed molds as part of the development, we achieve a better product quality, because we can test more, we can experiment more, our decision quality is improved. And that means that at the end of the day, we launch better products that have been tested more thoroughly. And this is also important to remember, we can adapt the product even after it's in the market by changing mold elements if we need to. Now, why would we want to choose systems from Raise3D for the 3D printed molds implementation? Well, what I like most about the printers, and this is my personal preference, is the robustness, the manufacturing quality of the things, because it results in a very high precision and repeatability. I've been running my Raise3D systems for almost a year now, and what I'm seeing is they don't really mess up my workflow. They are reliable in the printing, they are reliable in the cleaning and curing, and I get a uniform quality out, which is what I need in order to produce molds. I need the open materials mode, and the open materials mode that is provided with the off-the-shelf Raise3D package is very good. I don't need anything more than that, because I can easily adapt standard materials for my particular material preferences. I run a series of materials that are not standard, and these materials I can easily set up in the Raise3D system. That also means if you choose to adopt Raise3D systems, you can get those parameters from me. And then I like the workflow. Resin printing, which is what we do with 3D printed molds, is messy business. But if you have a workflow like the Raise3D workflow, where you don't have to really touch the resin as we move through the process, you're in a much better spot. The way the Raise3D workflow is laid out, you can basically configure all the parameters that you need in the slicer software, and then you can use the build plate with the build job on it as a token that moves through the entire manufacturing process, so you don't have to touch the parts. You don't have to get in touch with liquid resin, and this is a huge benefit. And then, of course, it's important to look at the price tag of the entire solution. I've been selling printer packages worth more than 200,000 euro when we started Addifab. You don't have to pay nearly as much for a Raise3D package, but the quality and the durability and the productivity is actually better than what we delivered at Addifab back in the days. Now, let's have a look at different things you can do with a 3D printed molds. And as I was talking about already in the beginning, one of the key use cases is where a material has not been translated to 3D printing. In the case of the drone propellers that we have also launched together with Raise3D, the objective is to get a carbon-filled LCP material into the hands of product developers. The trick with this specific material is that it is noise reducing, but the problem is we have no way to 3D print it with a sufficiently good surface quality and with a sufficiently high productivity. Using 3D printed molds to explore design concepts allows us to start injection molding prototype parts with a good surface quality, with a good precision, if we use the right printer systems. And I used the Raise3D system because I needed to manufacture quite a few molds for this particular application. Another important example is from a Danish manufacturing organization, which is known in most countries in the world. Danfoss is producing pumps. And one of the first cases we did with Danfoss back in the days was a particular connector, which had to be manufactured in a specific PPS, which is not available for 3D printing, and which would then afterwards have to be overmolded with a flexible thermoplastic elastomer. Conventional tooling would be possible to use, of course, but it would have required an investment on the order of 25,000 euro, and the tool design and manufacturing would probably take about 100 days. That's the days we got from Danfoss. Using 3D printed molds, we brought the lead time down to 10 days and the costs down by a factor of 10. And of course, with 3D printed molds, we are not set up for high volume manufacturing. But the benefit of exploring a design before you start cutting the serial manufacturing tool is you get hard evidence that you can mold the part and that it provides the performance you need. One important thing to remember about 3D printed molds is that if you can get a fully functional, performance-ready prototype, you will only get better when you migrate to metal. So the worst thing we can end up with in a 3D printed mold situation is a false negative, namely that we kill a product that might have been possible to do with conventional metal molds. But to date, I have not had that experience yet because we can usually find a way to make that migration work as intended. One of the key applications of 3D printed molds is in the manufacturing of spare parts. I know that a lot of marketing is going into communicating the relevance of 3D printing for spare parts manufacturing. And if we start combining the benefits of 3D printing with injection molding, we also enable the production of parts that are equivalent in materials and equivalent in manufacturing process to those original parts that were injection molded. And in some industries, this is of critical importance. I remember a dialogue with a couple of Airbus officials a couple of years ago where we were sort of talking about this 3D printed spare parts paradigm. And their key challenge is that if they need to start implementing 3D printed spare parts, they need to not only verify the performance of the part itself, they need to also look at the long-term durability. They need to look at the material's performance as it stays in the use environment. And this means that they have to basically revalidate the spare part as a new part. If they 3D print the molds and use the same material and injection mold instead of 3D printing, they don't have to go through the same painstaking re-evaluation, because they're not changing the material and they're not changing the manufacturing process. What they need to do is to verify that the part performs as intended, because there is nothing in the process that would justify the assumption that the part itself will change differently. And this is also exploited in the automotive industry. We had a case with a car manufacturer which was using a specific glass-filled PA material for a specific part, and where we were able to use 3D printed mold to make the replacement parts in the exact same material. A concept that is not universally recognized yet is the concept of personalized injection molded parts. Again, we may wind up in a situation where we require specific performance that is not achievable by 3D printing alone. And the case that I'm presenting here is that of a world-class Paralympic athlete who needed a prosthetic glove to continue his work. His first glove was made from carbon composite, which was manually created for him. But as that one started coming apart, he needed a replacement which had the same weight, the same shape, the same feel. We could digitalize the glove he had, but manufacturing with 3D printing would result in a part that was too heavy and too weak. And for that reason, we went into injection molding using a high-performance PPA material with a 30% carbon fill, which produced exactly the right feel and stiffness of the glove, which at the end of the day resulted in Peter Rosenmeier, the athlete, being able to continue his career. So even when we start talking about a single part, we can actually use this manufacturing paradigm with success. I have a background in medical device development and manufacturing, and for me, it's been a key priority to ensure that we can support medical device applications with 3D printed molds. For that reason, we did an assessment of the biocompatibility of parts that were manufactured with 3D printed molds, and we found that we would not be changing the biochemistry of the materials, and we found that we would not be leaving residues on the materials we injection molded, which means we can basically use this technology for the manufacturing of medical devices, and we can set up a protocol for the manufacturing of medical devices that can comply with regulatory requirements, and at the same time provide the scalability if we need to, that provides us with the ability to move into mass manufacturing. A hot topic in Denmark is the use of recycled materials. We've got several manufacturers of recycled materials. One particular manufacturer is using fish net that is recovered from the oceans. And we had a use case where a funding organization would like to provide some awards which had to be made from this particular recycled material. Since it's not easy to translate recycled materials to 3D printing because of the very, very hard to control quality of the materials, we used injection molding in 3D printed molds. And because we had the opportunity to dissolve some of the mold elements, we could manufacture the parts in a very, very complex design, as you can see. I'm not sure how many applications of latticed injection molded parts we have out there, but this one definitely shows that latticing is possible even with recycled materials and injection molding. And for recyclers, it's important to have access to mass market applications also, which means we need to help the recyclers gain injection molding quickly and efficiently. If we are just offering 3D printing, there is a barrier to the amount of scale we can offer. So this is also an important enabler for the recyclers to get the materials into the hands of high volume applications. And then, of course, depending on the industry, depending on the use case we are looking at, versatility comes in as an important parameter. We started out at Additive molding polypropylenes and TPE materials, but we quickly discovered that we could also handle high temperature, high fill thermoplastics. We could handle metal injection molding, we could handle ceramic injection molding, we could handle silicone injection molding. And this means that a manufacturing organization implementing 3D printed molds will right of a sudden be removing one of the most important barriers that we have in the additive manufacturing domain, namely the access to materials. My basic assumption, and I've proven that assumption in more than 800 projects, is that if you can mold a material using a conventional metal mold, we can also mold that material using a 3D printed mold. And as mentioned, to date, I haven't had a material through my tech stack that was not possible to mold using this approach if it was thermoplastic. We also have the opportunity of working with more complex assemblies. The Danfoss part that I showed earlier is an example of an overmolded part where you have a rigid body which is overmolded with a soft tightening material. But we also do 2K in the sense that you may have a metal insert that you want to embed in the injection molded part. I'm showing two examples here. One is of a material, a PPS frame, which we had to insert a metal lattice in and a metal liquid connector. And the other is the insertion of threaded screw inserts to enable a very, very tight, strong connection. This is also one of the things that is enabled by us not having to necessarily split the mold. We can also work with soluble inserts as an alternative, and that means we can incorporate very complex part architecture already in the prototyping stage. And then for those of you who have watched this presentation and started thinking that this might not be a bad idea to test, in collaboration with Shree, we are offering quite a few different packages. I've chosen to show three main configurations here. One which is very low cost, based on manual operation of the injection molding system, because that means we can go below $10,000 in the entire package. One which is intended for R&D departments where the injection molding machine is still desktop, but where we have more process control. And then for the industrial manufacturing, we would of course be using fully fledged injection molding machines like the 𝗪𝗕𝗕 that we are showing here, but the printer package could stay exactly the same because we are already at a quality level and a repeatability level that is good enough for these three applications. And then from the 3D molds perspective, I'll be happy to support your application and implementation by providing the training, the design assistance, and the other topics that we need to cover in order to get you off the ground quickly and efficiently. So that's basically what I had to talk about today. I think we should have enough time for a pretty comprehensive Q&A, and I look very much forward to having the talk with you.
Thank you, Las, for this exciting webinar. Thank you very much. So it was a very insightful presentation, and so let's move forward. Let's move on to the question and answer session. So please submit your questions via the Q&A section or the chat box, and I will read out these questions to Las, and he will answer your questions. Okay, so let's have a look at the questions we have. Okay, so we have questions from Kaustubh Kulkarni. These 3D molds are only one-time use, and how this justifies this cost. So Las, I guess you can see the question as well.
I can see the question, and it is not correct that they are one-time use. That depends on the part design and it depends on the material we are injection molding. I have been using 3D printed molds in the manufacturing of more than 100 parts per mold. And this means that whenever we start designing a new mold for a part, we always have to think about costs. My design philosophy with the mold design is to reuse as much of the mold as I can for as many shots as I can, and to dissolve or single use only those parts of the mold that stick in the molded part. So my cost per unit on a part that is molded in a 3D printed mold may be less than €1 a part, depending on how much I need to sacrifice. But thanks a lot for the question.
Okay. So the next question is from Kaustav again. How do we discard the dissolved resin?
That depends whether you actually dissolve. I have 4 different ways of getting parts out of molds now. My first is, of course, the splitting when that is possible. The second is applying a little heat before I split, because that turns my mold a little softer, which means it behaves like a silicone mold. The third is using hot water. And if I use hot water, I can just pour the water down the drain because the residues are not really contaminating. If I need to use sodium hydroxide or another alkaline, I dispose of it just as I dispose of the isopropanol that I'm using for the cleaning of my printed parts. I have a specialized waste stream for that, and I imagine that you have the same if you are resin printing.
Okay. Okay, thank you, Las. So, again, the question is from Kaustav. Any specific skills required to design the mold?
You will need to know how to operate a CAD workstation. And if you are designing parts, then you probably already know how to operate CAD. I can easily teach you how to design 3D printed molds that are cost optimized. So the key skill to have is a CAD operator who understands how to operate a CAD program. So knowing how to design a part, I can teach you how to design molds. And then, of course, you need to operate 3D printers and injection molding machines. But again, those are probably skills you either have or that somebody in your supply chain have. So for me, the critical skill is to have that CAD operator who knows how to design the mold. The rest we can set up. Make sense?
Okay. The next question is by Paresh. How do you handle the moving cores slash sliders?
That is a very, very good question. One of the key reasons why I use soluble mold elements is that I don't want to handle sliders and moving parts. A good 3D printed mold comes together like this and is separated like this, no matter how many side cores you need to pull out of it, because I am dissolving those elements that would normally require a slider. And this is one of the secrets in the mold designs we are pursuing. We don't want the complexity of the injection molding machine being set up to handle all these sliders. We don't want the mold design to be complex. The focus in the prototyping phase is on the part, and we design the mold to be as simple as possible. Once the part is proven, we can work out the mold design for the scale up in details. But we need to get the part right, and that means simplifying the mold design. I use soluble elements for everything that would normally require a slider. I hope that
Okay.
answered the question.
Yeah, I hope so. The next question is by Paresh again. What would be the typical mold life for polymers like PA66 plus GF or PCGF?
If the mold is easy to take apart, you should expect to get 5 to 10 parts out per mold. If your mold is hard to separate because you have part fixtures are locked in, we need to combine single-use mold elements with reusable mold elements. But this is for a PA6 with 30% glass, this is what I would expect to see. Of course, if the part is very big, your mold life expectancy also changes, but this comes down to the part design, basically.
Okay. So another question from again Paresh. So if want to 500 parts, we will have to produce 500 soluble inserts.
That is correct. If we have a feature or more features in the part that require side action. Again, like I said, if I'm molding a PP part or a part in TPE material, I may use only 5 molds for the 500. But if I'm molding a peak part with 3 undercuts and twistable screw insert, then I shouldn't expect to get more than a couple of shots out of each mold. But then remember, the inserts that I'm using will be small, and that means that I could potentially be manufacturing all the 500 inserts in one batch using the Raise3D and using perhaps, I don't know, 50 or 100 euro worth of material. And if you look at the cost of implementing a slider versus the cost of printing for 100 euro soluble parts, that investment in the slider may be hard to justify.
Okay. So another question again from Paresh. Do these molds have cooling channels?
And my answer to that is no, normally not. One of the benefits of 3D printed molds is they are very good insulators. And this is what is helping us when we are molding PPA or PEEK or PPS or other crystalline materials, because the cool down is very slow. But the same good insulation also means that adding cooling channels does not really make sense, because we don't transfer the cooling into the mold cavity very efficiently. When we are molding prototypes, we are not too concerned with the cycle time. We are concerned with the product quality and with getting something that is representative. Once we want to start scaling up, cycle time starts mattering. And that's when we migrate to metal molds. But for the prototyping, we need rapid, cheap tooling, and then we accept a slightly higher cycle time. Hope that makes sense.
Yeah, that makes sense. So the next question is by Rachana Mane. Can we make 3D printed molds on a large scale? What is the maximum size as of now?
Well, with Wilson Sporting Goods, I've been involved in injection molding baseball bat cores that are about 80 to 90 centimeters long. So it's not the 3D printed mold that is the limitation. We need to investigate what are the costs of a 3D printed mold versus how many parts can we get out of it. I also have customers who are using 3D printed molds in combination with CNC milled parts, because by doing that, they can simplify the metal mold design, but they can still maintain the design freedom. And if you are talking about very large parts, you don't want to start 3D printing the entire mold. You 3D print those parts of the molds that are hard to design the mold for. So the size is not a limitation, but cost may become an issue we need to manage by designing the right way.
Okay. Okay, the next question is by Sandeep. Which software is used for designing 3D printed molds? Is it free or need license?
Normally, my customers use the CAD software they also use for designing their parts. I have a lot of customers using Autodesk, Fusion 3D, SolidWorks. We are in the process of developing software that will help users design the molds. But most companies working with us already design the parts in a CAD software, and this CAD software can export the files in a format that we can work with, normally step or similar.
Okay.
So you can use FreeCAD, you can use Blender if that is what you're using, and then we can design the molds in the same software. That's not a problem.
Okay, so the next question is again related to size by Jagmohan. What is the maximum size of mold we can make?
With the Raise3D, we have a build height of about 400 millimeters. We've got a build area of about 200 times 150, and then we can start putting together molds. When we were working at Adifab, we had a 50-ton cast-buffet. We had customers using 300 or 400-ton machines for the injection molding. So again, I don't think the printed mold is the limitation. It's very much about figuring out, is this cost efficient, or do we need to think a little bit differently? But with the Raise3D, we can make molds that are easily 400 by 400 by 300 millimeters without having problems. So that's fairly sizable.
Okay. So GK Venu has a question. Internal combustion engine components will support 3D printing mold.
I think the answer to that is a yes. I would like to know which materials we would start working with. And if we are talking about metal or ceramic, the supply chain is a little bit more specialized. But I have customers who also use this technology for metal injection molding of titanium alloys or stainless steel alloys. And the technology is also useful for that if you know how to operate the rest of the equipment. I'm not sure I answered the question, but my answer would be yes, depending on the material, the size of the part. If you're talking about the entire engine block, I'm not sure that that would be the best way to apply what we're doing here.
Okay, so we have another last question for this session. That is, which is more preferred, a soluble mold or two-part core and cavity mold?
And my answer to that question is both. When I can make a two-part mold, I make it and I don't dissolve anything. I use the soluble option only when I have to, because I also need to mind my costs here. Everything I do, I have to pay for myself, which means that when I design a mold, I want it to be as cheap to manufacture and use as possible. But I also want to be able to do complex parts in complex materials. And for that, I use this combination of soluble and non-soluble. But non-soluble is perhaps 80 or 90% of the mold, and then 10% is soluble, or 5% is soluble. So it depends.
Okay, so yeah, last, you can continue.
Yes, it depends. And my advice to you is, if you have a specific part or a specific product you would like us to review, please reach out to your shreerapid representative. I'll be very, very happy to conduct a free of charge design review and to provide my input on the best way to approach the part or product using 3D printed molds. We can talk about the costs of manufacturing. We can talk about lead times. I can help you understand where is the complexity, where would we need durable materials, where would we use soluble, so you have an understanding of what we can do before you start deciding how you want to do it.
Okay, so we got the last question again. Is peak molding possible? What is the solution for it in terms of mold material and injection molding machine?
I have very good collaborations with Victrex in the peak domain. I also have a very good dialogue with Evonik about the peak domain. The baby plast that I have here behind me goes to 425 degrees C, so I can injection mold peak. And with a soluble or non-soluble mold, I can also process the peak 3D printed. This is something that I can very happily support further dialogue about. I have peak materials in stock. I have got the Victrix 450G, a couple of Solways, some Evonik. So I'll be more than happy to talk about peak.
Okay. Okay. Okay, Las. So I think we have come to the end of this session. So thanks a lot, Las, and a heartfelt gratitude for sharing this deep expertise and valuable insights and giving us an immense knowledge about molds. Special thank you to Sri Rapid Technologies team as well for organizing today's webinar. And of course, a big thank you to of you attendees who have participated in the poll and also asked good questions. If you like to connect with us, please you can connect us at marketing.shreerapid.com or on the given number on your screen. Also, we have our customer innovation center in Mumbai. So if you want to explore or benchmark any parts or scan or develop CAD files or even experience a fully digital manufacturing workflow, we are available in Mumbai, in Andheri East, basically at Raj Industrials. You can connect with us and also you can contact us on the same so we can arrange a visit for you. So thank you all of you again. Also, before signing off, please request you to fill out the post-webinar feedback survey. We look forward to having you join us again in our upcoming webinar. Thank you. Also, we will be sending you the PPT as last mentioned in the attachment and the materials section. You can see the PPT which was presented by LAS and you can refer it. And after referring, if you have any questions or if you have any queries about the same, you can connect with us. So we have uploaded the same. I hope it is available to you and you can see it in the materials session. Okay, Las, thank you so much. Thank you, everyone. And hope to see you in the next session. Thank you.